Good day, everyone. I'm Norman Wildberger. We're looking at box arithmetic. Today I want to give some applications of relatively simple box arithmetic at the polynumber level to an interesting topic in modern algebra / analysis / number theory / combinatorics, namely Q-series. Now, if you're interested in this topic and want to know more about it, I have an entire series on this topic in the Wild Egg Mathematics Courses channel. So the story of Q-series perhaps starts with Euler's Pentagonal number theorem, which is a formula for obtaining a certain sequence of numbers called pentagonal numbers, which are sort of five-fold analogs of triangular numbers. And the formula is given by this infinite product, 1 minus alpha to the n, and going from 1 to infinity. Okay. 1 minus alpha times 1 minus alpha squared times 1 minus alpha cubed, etc. And as I've explained also in my Wild Egg Maths courses, in the advice for research mathematicians there, I talk about processes and a kind of convergence of processes that can allow us to think about what's happening with the identity in something like this without having to resort to, infinite completed processes. So what we're doing here is we're trying to expand this much as if it was a polynomial and looking at various powers, and happily any particular power like alpha to the 5 only occurs a finite number of times. It's the critical thing that allows you sort of to have a well-defined result of this thing. And it's a very interesting sequence with plus and minuses and these rather interesting numbers. And it's particularly important because of a remarkable connection that Euler realized with the partition function. So if P of n is the number of partitions of n, the number of ways of writing a natural number as a sum of other natural numbers, like P of 5 is 7, because you can write 5 as 5, or 4 plus 1, or 3 plus 1 plus 1, or 3 plus 2, or 2 plus 1, or 2 plus 1 plus 1 plus 1, or 1 plus 1 plus 1 plus 1 plus 1. So this actually gives a recursive way of computing this P of n function, and you see that these terms here correspond exactly to the exponents and the signs that are appearing up here. Okay, so the question we want to address today is, can we express this kind of ongoing identity in the context of box arithmetic? So a good place to start is with a finite version, and we'll just have a quick review of box arithmetic. So if we just look at the first two terms, 1 minus alpha times 1 minus alpha squared, that's 1 minus alpha squared plus alpha cubed. So how might we express that in box arithmetic? First of all, a quick review. So in box arithmetic, these days we have two zeros, the black 0 and the red 0. So this is 0 and this is anti-0. And one of my viewers made the interesting suggestion that I should think of something that makes the red a little bit more visible to the black for colorblind people. So I'm going to try to make this red box typically more oval shaped, so it'll have rounded corners and perhaps be a little bit thicker. So hopefully that will distinguish it more clearly from the black ones, which are going to be right-angled, sharp rectangles. Okay, so those are the zeros, and then a natural number is a box of zeros, and the boxes can be either black or red boxes. So this thing here is the basic new object, a box inside a box. So that's like a box containing 0. That's the definition of the number 1. While the number 2 is a box like this with two black boxes inside it. And if we have a black box with a red box inside it, then that's minus 1. Or anti-1. And the crucial thing is that if you add this box to this box, by that we mean we dump out the contents into another box, okay, then the black box and the red box being inside the same box, they annihilate. That's the crucial particle-antiparticle property of these black and red objects. Okay, so that's why we get minus 1. Okay, and then going down one level to the polynomial version, or polynumbers as I prefer to call them. If we have a box inside a box inside a box, so that's a box containing 1, that's a new object, we'll call it alpha. And then minus alpha you get by making red the top innermost box. Okay, if we make the inside box red, then we get alpha to the -1. Here's what alpha squared looks like, and so on. Okay, so now let's look at 1 minus alpha times 1 minus alpha squared. Okay, so here is 1 minus alpha. It's a box containing an empty box there, so that's like the number 1. If this thing wasn't here, that would be the number 1. And if this thing wasn't here, we would have minus alpha, this one right here. So this is the combination of this one and this one, the sum of this one and this one, 1 plus minus alpha. If we take 1 minus alpha squared, then we are taking the sum of this one, then we're taking the sum of this one with minus alpha squared. So minus alpha squared is obtained by taking this thing and making red that biggest inner box, okay, namely that one there. So how do we multiply boxes? Well, we just take all possible sums of entries in this box and entries in this box. So this one here, this is 0 plus 0 is 0. 0 plus this is just this. This plus 0 is just itself. So the only otherwise interesting one is this box with this box. So we have a red box with a black one inside it, another red box with 2 black boxes inside it, and we're adding them. Well, to add boxes, we dump them all in. So we dump them all in, we're going to get 3 black boxes. But what is the color of the bounding new box? That's determined by the number of red boxes that are contributing to the sum. There are 2 red boxes contributing to the sum, so it's like a parity kind of thing. So the 2 odds make it even, and we get a black box as a result. Okay, and then we confirm that that is indeed the same as 1 minus alpha squared plus alpha cubed. So this is a way of doing it with a very primitive sort of assembly language box arithmetic. Let's have a look at the same computation, but just at a little bit higher level, by looking at polynumbers as boxes of natural numbers. Okay, so 1 minus alpha in terms of that would be a box with a 0 and a 1 ante. The 1 ante is a red box with a black box inside it. A black box with a black box inside it is 1. A red box with a black box inside it is the ante of 1. That's a new kind of mathematical object that hasn't been in existence up till now. Okay? But it's playing an important role because it's a constituent of this box here to create this element for us in a box setting. And similarly, 1 minus alpha squared is the box consisting of 0 and 2 ante. So when we multiply these, we have to add all possible ingredients. So 0 plus 0 is 0. 0 plus 2 ante is 2 ante. 1 ante plus 0 is 1 ante. And 1 ante plus 2 ante is like 1 plus 2. That's 3. But is there an ante or a not ante? Well, there's an ante and an ante. There's 2 antes. They sort of cancel out. And we just have a single 3. So again, we get 1 minus alpha squared plus alpha cubed. But this will be a little bit easier for most people to recognize because it's very much just like doing integer or natural number arithmetic with the proviso that there are these antes floating around. So we have to sort of take proper care of them, but that's not too hard. So here's another example, just going up one more degree. 1 minus alpha times 1 minus alpha squared times 1 minus alpha cubed. So there's 1 minus alpha, there's 1 minus alpha squared, and there's 1 minus alpha cubed. And then when we form the product of these things, we have to form all possible sums. Okay, like 0 plus 0 plus 0, that's 0. The ones involving 2 zeros are 1 ante plus 0 plus 0, that's 1 ante, or 0 plus 2 ante plus 0, that's that one, or 0 plus 0 plus 3 ante, that's 3 ante. The ones just involving a single, like 0 plus 1 ante plus 2 ante, that's 3, or 0 plus 2 ante plus 3 ante, that's 5, or 0 plus 1 ante plus 3 ante, that's 4. And finally, 1 ante plus 2 ante plus 3 ante is 6 ante because there's an odd number of antes. Okay, so there are 8 constituents altogether. That's 8 different possible sums of taking one element here, one element here, one element here. Now, of course, at this level here, we see the crucial cancellation. This 3 and this 3 ante are going to mutually annihilate each other. Crucially, they do not give us a 0. We're not getting 0. We're getting nothing, like a real nothing, okay? Not just a symbol for nothing, which is in fact something. We're just actually getting nothing. Just completely disappears. And we just get 0, 1 ante, 2 ante, 4, 5, 6 ante, which is the same as 1 minus alpha squared plus alpha to the 4th plus alpha to the 5 minus alpha to the 6, which is what you get when you expand this thing out. Okay, so now let's make the big jump to try to understand Euler's pentagonal formula in this context of box arithmetic. But definitely we have to step outside the bounds of what we've been doing up till now, because now we're not just working with finite numbers of finite objects, because we have this unbounded product and this unbounded sort of sum as the result of it. But nevertheless, we can understand this in the context of box arithmetic in a modest fashion, in a modest sort of unbounded fashion. So we don't pretend that we can go to infinity or any nonsense like that, okay? We recognize and respect the ongoing nature of both this product and this sum. But we have a precise meaning to the identity of this equaling this, in the sense that, you know, of equating the number of times a given object appears on the right-hand side and on the left-hand side. Okay. So how does that go? So, well, here's the 1 minus alpha squared, 1 minus alpha cubed, 1 minus alpha to the 4th, etc. Okay, so we have all of these things, and we have to take this unbounded product. So what we mean by that is we're going to take sums, okay, but we're going to take sums that we can actually do, and we really can only do finite sums. So that means that we have to insist that the entries that we take are mostly zeros. In other words, we're only going to take a finite number of non-zero entries in this sum. We're just doing addition, okay? But we're not allowed to say, okay, what is this 1a plus this 2a plus this 3a plus this 4a, etc. We're not taking that kind of sum. We're only taking a finite number of any of them, okay? That's by agreement. That's what we mean, okay? And so then what we can do is we can tabulate how many times we get various things. Okay, so when we look at this thing here now, there's only one way of getting a 0. 0 plus 0 plus 0 plus 0. To get a 1 or a 1 ante, there's only one way of doing that, to take that 1 ante and the others are chosen to be zeros. To get a 2, only the 2 ante there and zeros elsewhere. To get a 3, well, we could do that in one way by taking that 3, only that 3, so when I just say that 3, it means the rest zeros. Or we could take this 1 ante and that 2 ante. If we add those, we're also going to get a 3. Because 1 ante plus 2 ante is 3. So we're going to get a 3 ante as well as a 3, and they're going to annihilate each other. That's why there's no 3 here. Why is there no 4? Well, because there's a 4 ante that we get just by taking that one by itself. Or we could take this 1 ante and this 3 ante. When we add them, we get 4. That's going to cancel with this 4 ante. So there's no 4 in there. How about 5? Well, there's a 5 ante sitting there, so we can take that 5 ante. Or we could take a 1 ante and a 4 ante. That would actually cancel with that one. Or we could take a 2 ante and a 3 ante. So that's 1 5 left over. That's why there's a 5 there. Okay, and then we can carry on to make this calculation. But it's not, you know, a priori clear what the pattern is. This pattern here is very regular, but the pattern that it generates is, you know, pretty interesting, although Euler figured out what the pattern was, and it was a very interesting and important pattern, but it's not entirely obvious at first. So this is a calculation that should be done in quotes. It's not covered by what we've talked about in box arithmetic so far. It's an extension of what we've been doing, and it involves sort of unbounded or open boxes, so I'm sort of leaving this one open, you know, suggesting that the thing carries on. To me, it would be some kind of intellectual dishonesty to put a bar there and to pretend that this is a closed thing, that we can get the entire thing. No, it just keeps on going beyond our view. That's the honest historical way of thinking about such sums. Now, of the many hundreds of remarkable formulas in Q-series, I'm going to just choose one more here to talk about today, which is also due to Euler and also a very interesting and important discovery of his. It's concerning a very similar kind of product of 1 plus alpha to the n now. So a plus sign here. So we have 1 plus alpha times 1 plus alpha squared times 1 plus alpha cubed. And that turns out to be this series that starts this way with 3 dots, of course. 1 plus alpha squared plus 2 alpha cubed plus 2 alpha to the fourth plus 3 alpha to the fifth plus 4 alpha to the sixth, and it keeps going in some fashion, which is not entirely obvious. And remarkably, Euler realized, first of all, what the significance of this thing was, that this was counting something pretty interesting. In fact, it was counting the number of partitions of an integer n into distinct parts. So 5 can be subdivided or partitioned into distinct parts, either as 5 or as 4 plus 1 or as 3 plus 2. Okay? And the other ones don't count, like 2 plus 1 doesn't count because it has 2 repeated 2s, or 3 plus 1 doesn't count, etc. So there's only 3 partitions of 5 into distinct parts. So that's what that's counting. And he, by a little bit of clever algebraic manipulation, was able to convince himself that this is actually the same as this product of 1 over 1 minus alpha to the 2n minus 1. So we're taking the sort of fraction 1 over 1 minus alpha times 1 minus alpha cubed, 1 minus alpha to the 5. And in this context, it turns out that this is then allows him to deduce that this number is also equal to the number of partitions of n into odd parts. So for example, 5 is equal to 5, and it's also equal to 3 plus 1 plus 1. All the parts are odd, or it's equal to 1 plus 1 plus 1 plus 1 plus 1. All the parts are odd. There's 3 of those. So these two numbers are the same, and that's not at all obvious, but it's a result of this algebraic identity here, because these two series are encoding these two things. So this remarkable work done in 1740. So let's have a look at this first thing. How would we think about this from a box point of view? So 1 plus alpha now is the box just containing the numbers 0 and 1. That's what we think is the polynomial or polynumber 1 plus alpha sort of fundamentally. It's just this box with a 0 and a 1 in it. Here is 1 plus alpha squared, here is 1 plus alpha cubed. And you do the same thing, you look at all possible, and you do the same thing, you look at all possible kinds of sums that you can get by taking finite numbers of non-zero entries here, and you get a 0 in one way, you get a 1, you get a 2, you get a 3, however, in 2 different ways. And here I'm going to use that notation that I introduced some time ago. We'll put a little 2 as a left sub-index here to denote a multiplicity. So instead of having to write 2 different 3s, I'll just write a 3 with a 2 underneath. So that means we have 2 3s floating around. And what are those 2 3s? Well, we could either take that 3 there, or we could take 1 and 2. 4, there are 2 ways of getting that. We could choose the 4 here, or we could choose the 1 plus 3. And then there's 3 5s, 4 6s, 5 7s, 6 8s, 10 10s, etc. So this is an alternate way of thinking about representing the information in this. So let's stop and pause for a minute and think. I know this is very unfamiliar to us, but sort of logically and objectively, if we can be, which is really more essential. You see, when you're taking these products here, okay, we have these exponentials. First of all, there's the question, if I ask an ordinary mathematician, what do you mean by alpha here, or in the usual story, Q? Okay, what is Q? Well, Q sometimes means this, and sometimes it means that, and sometimes it means something different. Okay, and it's not so easy to say what a variable is in mathematics. Even a a computer scientist has some, there's all kinds of possible ambiguity as to what that term actually means. But for us, this alpha is just, being represented by this box with the 1 in it. So it's completely cut and dried. And furthermore, when we do this multiplication, like alpha squared times alpha cubed, okay, that's alpha to the 5th. But it's really an addition, isn't it? I mean, yes, we're saying we're doing multiplication, but computationally, it's really an addition. So what's happening here is closer to the computational heart of what we're really doing. And moreover, you can see that it's more efficient to represent what's going on because these alphas in some way are extraneous, right? They're not really an essential part of the story. They're sort of placeholders or ways of pinning these exponents to something. But here there are no alphas, and also there are no plus signs. Okay, so just have a look at the compression here, right? I mean, in this piece of information, I've compressed, I think, the data a lot more efficiently. So, my guess is that these little Tic Tacs that are flying around in our neighborhood, all these little aliens, perhaps that are living under the water or whatever, that we're soon probably going to be chatting with, in the next few decades. My guess is that, this might actually be more in keeping with what they do. We'll have to ask them when we start having serious chats with them, won't we? And what about that expression that happened in the denominator of Euler's formula? The 1 minus alpha times 1 minus alpha cubed times 1 minus alpha to the 5th, etc. Product of 1 minus alpha to odd powers. So that turns out to be, at least the first few terms, 1 minus alpha cubed plus alpha to the 4th minus alpha to the 5th plus alpha to the 6th, and so on in some fashion, which is not at all obvious. So from a box point of view, this is 0, 1 ante box. This is a box with 0, 3 ante. This is a box with 0, 5 ante. And again, we just do the all possible sums where we're just taking finite numbers of entries. So never more than a finite number of non-zero entries. So there's a single way of getting a 0, and there's a 1 ante, there's a 3 ante. There is a 4. That's sum 1 ante plus 3 ante is 4. There's a 5 ante, there it is. There's a 6, because the 6 is appearing not over here, but it's appearing as 1 ante plus 5 ante. Okay, and that's ante plus ante, so that's just a regular 6. And then there's a 7 ante, and then there's 2 8s, and then 2 9 antes, 2 10s, 2 11 antes, etc. You can kind of get the idea that the odd numbers are all appearing with antes, so that should also have an ante. And then the identity that the first product was equal to 1 over the second product really amounts to the expression that that first big box that we got times this second big box that we got. Okay, when we multiply these two, we should just get 1. So that's a remarkable thing, okay? So there's some interesting but non-trivial pattern here. There's another interesting but non-trivial pattern here. Okay, so what happens when we multiply these two things? So 0 plus 0 is 0. 0 plus 1 and 0 plus 1 ante, so we get a 1 and a 1 ante. They cancel, so there's no 1s. 2s. There's a 0 plus 2, that's 2. And 1 plus 1 ante is 2 ante. So that 2 and that 2 ante cancel. 3s. Well, there's 2 3s here, so 0 plus 3, there's 2 of them, so we get 2 3s here. But we also get a 3 ante here. Okay. But we also get 1 ante plus a 2. That's another 3 ante, so all the 3 antes cancel. And the same thing happens with every single natural number. Go through it, every single number is canceled with something else. And at the end of the day, the only thing that's in this big product is the single 0 that we got by adding that 0 and that 0. So the box containing 0 is 1. And that's the content of Euler's identity. So It's an interesting alternate way, which one can argue cuts closer to the chase of what we're really doing arithmetically, which circumvents the need for elaborate discussion about the roles of variables, and which is simpler notationally. At least I think one can argue that. And it's fascinating that these anti-objects play an important role in this arithmetic. Nevertheless, you can say, yes, okay, so you're redoing something that's well known in a different way with different terminology, and that's right. But in my next video, I'm going to give you another application of box arithmetic to another aspect of number theory, actually also a very important formula of Euler's, having to do with the Riemann zeta function. And we're going to see, in this case, a highly non-trivial and novel understanding of what's going on with a very important number theoretical situation by taking this box arithmetic point of view. I hope you'll join me for that. I'm Wildberger. Thanks for listening.